Take any room, remove all the furniture, pump out all the air molecules, eliminate every atom. What's left? Nothing, you say? Empty space, a vacuum. But what is nothing? Is it just the absence of things? Can absence have properties? Can it weigh something? Can it bend? We say empty space like we know what we mean, but that's just a label for our ignorance. The real answer requires abandoning the idea that space is a container at all. Empty space isn't empty, but the reason has nothing to do with quantum fluctuations or virtual particles. It's about what space itself is. Everyone imagines space as a container, a stage, a box, a backdrop where things happen. You have the stage, you have the actors. Remove the actors, the stage remains, empty, waiting. This seems obvious, doesn't it? Intuitive. The very word space suggests roominess, a place for things to be. But suppose space isn't a container. Suppose it's something else entirely. In 1887, everyone believed light needed a medium to travel through. The luminiferous ether, they called it. It made perfect sense. Waves in water need water. Sound waves need air. Light is a wave, so light must need something to wave in. Two American physicists, Albert Michelson and Edward Morley, built an ingenious apparatus to detect Earth moving through this ether. If we're plowing through an invisible medium as we orbit the sun, there should be an ether wind. Just like how you feel wind when you stick your head out a moving car, even on a calm day. They found nothing. No ether wind. No medium. The experiment was repeated, refined, checked again. Same result. Most physicists said, "We need better equipment. The effect must be smaller than we thought." I said, "What if there is no ether? What if light doesn't need a medium at all?" Which immediately raises a question. If there's no medium, what determines light speed? Sound travels 340 meters per second in air. But relative to what? Relative to the air itself. If you run toward a sound, you hear it at 340 plus, your running speed. Run away, you hear it at 340 minus your speed. That's how waves in a medium work. Light travels at 299, 792, 458 meters per second. Relative to what? Not relative to a medium. We just established the medium doesn't exist. Here's the strange part. Relative to you. Always. No matter how fast you're moving. You can be standing still. You can be rushing toward the light source at half the speed of light. You can be fleeing from it. You always measure light moving at exactly the same speed. How is that possible? If you chase a light beam at half its speed, shouldn't it look slower to you? Something must be wrong with our assumptions. Either light speed changes depending on your motion, but experiments say no, it doesn't. Or our measurements of space and time change instead. Not our measurements, space and time themselves. The essential point is this. Space and time aren't fixed containers, absolute and unchanging. They're flexible. They're dynamic. A moving clock actually runs slower than a stationary one. This is called time dilation. A moving ruler actually contracts in the direction of motion. Length contraction. This isn't an illusion, not some trick of perception. It's geometry. The geometry of space-time itself changes depending on your motion. When I first proposed this in 1905, people thought I was joking. But the mathematics was clear. The logic was unavoidable, and within a few years, experiments confirmed it. Moving particles live longer before they decay. Moving rulers really are shorter. The effects are tiny at everyday speeds, but at high velocities, they're dramatic and measurable. Now think about what this means. Once space and time can stretch and bend, they're not nothing. anymore. Nothing cannot bend. Nothing cannot stretch. Nothing doesn't have properties. Only something can be measured, can change, can vary from place to place. And if space can bend, what bends it? Mass and energy. Heavy objects create curves in the geometry of space-time. Imagine, well, actually, we shouldn't imagine the rubber sheet analogy. That's misleading. But the essential point is that what we call gravity isn't a force pulling you down. It's the geometry of space-time being curved by Earth's mass, and you following the straightest possible path through that curved geometry. You feel like you're being pulled, but you're just moving along a geodesic, the space-time equivalent of a straight line. We see this. Light from distant stars bends when it passes near the sun. Arthur Eddington measured this during the total solar eclipse of 1919. The deflection matched my predictions exactly. 1.75 arcseconds at the sun's edge. Not approximately. Exactly. So space isn't empty because it's filled with gravitational field. Every massive object in the universe contributes. The sun curves space-time around itself. Earth curves space-time around itself. You curve space-time around yourself. Imperceptibly, but really. The field has energy density. It's measurable, real. Even far from everything, far from any particular mass, the field still exists. The gravitational influence of distant galaxies, the overall curvature of the universe, it's all there. Actually, more precisely, space is the field. They're not separate things. The sun doesn't create a distortion in space, like a ball pressing down into a rubber sheet. Space around the sun is the distortion. The geometry itself is the gravitational field. When we describe space-time using mathematical coordinates, the metric tensor, the object that tells you distances and angles, that is the gravitational field. There's nothing underneath space that gets bent. Space is the thing that bends. This is difficult to visualize because we're used to thinking of fields as something in space. But space-time is the field. Now, quantum mechanics adds another layer. According to Heisenberg's uncertainty principle, you cannot simultaneously know a particle's exact position and exact momentum. But it goes deeper than that. Energy and time have an uncertainty relation too. For a very brief interval of time, energy can fluctuate wildly. Even in empty space, in what we call a vacuum, the quantum fields that permeate space are jittering, oscillating, never quite settling down to zero. These fluctuations manifest as virtual particles popping in and out of existence. An electron and positron appear, exist for a moment, annihilate back into the vacuum. This happens everywhere, constantly. The vacuum has energy density from these quantum fluctuations. When we calculate this energy density using quantum field theory, we get a catastrophe. The theory predicts a value roughly 10⁻120 times larger than what we observe. That's 1 followed by 120 zeros. It's the worst prediction in the history of physics. We call it the cosmological constant problem, and we still don't understand it. But something is there. We know this because the expansion of the universe is accelerating. Distant galaxies aren't just moving away from us. They're moving away faster and faster. This acceleration requires energy, and that energy appears to be spread uniformly throughout space. We call it dark energy, and it accounts for about 68% of the energy content of the universe. Empty space has weight. It has pressure, negative pressure actually, which causes the acceleration. So what is a vacuum really? Not absence, not nothing. It's the lowest energy state of all the fields. Gravitational field, electromagnetic field, all the quantum fields. These fields have ground states, minimum energies, structures. When we say empty, we mean no excitations above the ground state, no particles, no waves, no disturbances. But the ground state itself is rich, complex, geometric. It has energy density. It has physical properties. This isn't philosophy or speculation. It's measurable. Consider the Casimir effect. Take two flat, uncharged metal plates and place them very close together in a vacuum, just a few micrometers apart. They experience an attractive force pushing them together. Why? Because the quantum electromagnetic field between the plates is constrained. Only certain wavelengths fit between them, like standing waves on a string. Outside the plates, all wavelengths exist. This difference in the quantum vacuum creates a pressure difference, and the plates get pushed together. The force is tiny, about the weight of a dust mote, but it's real. Henrik Casimir predicted this in 1948, based purely on quantum field theory, measured in the laboratory in 1997. Real effect. If space were truly nothing, this couldn't happen. You can't constrain nothing. You can't create pressure differences in absence, or gravitational waves. When massive objects accelerate, like two black holes spiraling into each other, they create ripples in space-time itself. The geometry oscillates, stretches, and compresses, like a water surface disturbed by a stone. These waves travel at the speed of light, carrying energy with them. In September 2015, the LIGO detectors in Louisiana and Washington state detected gravitational waves from two black holes that collided 1 billion light-years away. Space-time rang like a bell. The detectors measured the oscillations, changes in distance smaller than the width of a proton, but unmistakably real. If space were nothing, it couldn't ripple. Nothing doesn't oscillate. The detection of gravitational waves proves definitively that space-time is a physical thing with dynamics, not an abstract mathematical convenience. Return to the question, with deeper understanding now. Space has geometry. Geometry can be flat or curved, can have different mathematical signatures. Euclidean geometry works for everyday distances on flat surfaces. The geometry you learned in school, where parallel lines never meet, and the angles of a triangle sum to 180 degrees. Minkowski geometry describes flat space-time with time as a fourth dimension, where the distance between events includes both space and time with a specific mathematical relationship. Riemannian geometry describes curved spacetimes near massive objects, where the curvature changes from place to place. The geometry can have topology, global shapes and connections. A sphere has different topology than a flat plane. You can walk around a sphere and return to where you started. On a flat plane, extending infinitely, you never return. The universe might be topologically flat, or it might curve back on itself in ways we haven't detected yet. We don't know. Empty space in our universe is flat on large scales. As far as we can measure, the overall curvature is zero or very close to it. But it's curved locally, near massive objects like Earth and the Sun, and it's expanding everywhere. The expansion means that distant points in space are getting farther apart, not because galaxies are moving through space, but because space itself is growing between them. New space is being created. The geometry is evolving. This geometry is physical. It affects how things move, how time flows, how light propagates, how energy distributes itself. You cannot understand motion without understanding geometry. Physics is geometry. We lost something with this realization. We lost the comfort of Newton's absolute space and time, the fixed stage, the unchanging backdrop where physics happens independently of what happens. That picture served science well for 2 centuries. It's intuitive. It matches everyday experience, but it's wrong. Space isn't a passive container. It's an active participant in physical processes. The geometry tells matter how to move. Objects follow geodesics through curved spacetime. Matter tells the geometry how to curve. The stress-energy tensor determines the curvature. They're coupled, inseparable, each affecting the other continuously. John Wheeler, an American physicist, put it perfectly. Spacetime tells matter how to move. Matter tells spacetime how to curve. That's Einstein's field equations in one sentence. But we gained something stranger and more profound. A unified view where geometry and physics are one thing, not two. The shape of space is not separate from the forces acting in it. The metric of spacetime, the mathematical object that tells you how to measure distances, is the gravitational field. The curvature, the deviation from flat geometry, is the source of tidal forces that stretch and squeeze objects. Everything is geometry, and geometry is everything. That's the essential insight that took me 10 years to develop fully, from special relativity in 1905 to general relativity in 1915. Geometry and physics are aspects of the same reality, described by the same equations, measured by the same experiments. When you measure how much a clock slows down near a massive object, you're measuring space-time curvature. When you watch an apple fall, you're watching it follow a geodesic through curved space-time. When you imagine an empty room now, what do you see? Not nothing. Not absence. You see geometric structure with minimum energy, quantum fields sitting at their ground states with irreducible quantum fluctuations, the fabric of space-time itself with its own dynamics and properties, still expanding from the Big Bang, carrying everything along with it, still curved by the mass of Earth beneath your feet, about 1 part in a billion compared to flat space, but real and measurable. Still curved by the sun, 150 million kilometers away. Still influenced by all the galaxies beyond. Their gravitational fields extending across the cosmos. Still capable of rippling if a gravitational wave passes through. Oscillating at the frequency of the wave. Still jittering with quantum fluctuations at the smallest scales. Still filled with dark energy. This mysterious uniform energy density that makes up 68% of the universe and drives the accelerating expansion. The emptiest vacuum we can create in a laboratory contains all of this. We can pump out air molecules, eliminate particles, cool the system to near absolute zero. But we cannot eliminate the geometry. We cannot turn off the quantum fields. We cannot remove the dark energy. Those are intrinsic to space itself. Even the vast spaces between galaxies, the most empty places in the universe, where matter is spread so thin that there's maybe 1 atom per cubic meter on average, are not nothing. They have geometry that's evolving, expanding. They have quantum field ground states. They have dark energy pushing them apart. They have a gravitational field from all the matter in the universe. Space there is as something, as space here. What determines this geometry? Why is space 3-dimensional and not 2 or 5 or 11? Some theories suggest extra dimensions exist, but are curled up too small to detect. Why does time flow forward and not backward, or both, directions equally? This connects to entropy and the arrow of time, the second law of thermodynamics. But the deep reason remains unclear. Why does the cosmological constant have the precise value it has, approximately 10 EWAS on 122 in natural units? Why not zero, which would seem more natural? Why not vastly larger, which quantum field theory predicts? If it were much larger, the universe would have expanded so fast that galaxies could never form. We wouldn't be here to ask the question, is that the answer? The anthropic principle? Or is there a deeper explanation we haven't found? Why did the universe start expanding at all? What was the Big Bang? The equations of general relativity describe a singularity, a point of infinite curvature. But we don't trust that prediction because quantum mechanics should become important at those scales. And we don't have a theory that unifies quantum mechanics with general relativity. Those are different questions, deeper questions. They push beyond what we understand. I've got to stop somewhere. The geometry goes deeper than we've mapped. Perhaps someday, someone will find the equations, maybe a theory of quantum gravity, maybe something stranger, that explain why space-time has the structure it does, why the laws take the form they take. For now, we can measure space, map its curvature, predict how it behaves in different situations. But the origin of the geometry itself, why there is something rather than nothing, why that something has the particular properties it has, that remains a mystery.